Hi everybody. In this video we're going to be looking at some applications of using the exponential functions. The application that we're going to be focusing on is one that involves compound interest. That is, if you were to take some money and put it into the bank, and the bank is going to pay you interest for having your money in there. Okay, how do they go about calculating the money that they're going to give you? So we're going to look at two formulas for compound interest. All right, so let's study the variables that are involved in both of these equations. After t years, so t will represent the number of years we're going to leave our money in the bank, the balance A in our account with principal P. P is the amount of money that you're going to put into your savings account. An annual interest rate R. R represents the rate. It has to be given in decimal form. Okay, it's given by these two formulas. All right, if the bank's going to stop and compound your money n times per year, okay, meaning that if they stop after 6 months or every 4 months and calculate your interest, this is the formula that they will use to calculate that amount of interest. So the amount A that you'll have in your account is equal to P, what you put in, times 100% of your money. That's what 1 stands for, 100% of your money, plus the rate that they offer divided by the number of times per year they stop and compound your interest, all raised to the number of compoundings times t, the number of years that you leave your money in the account. Most banks will use this compound interest formula right here. Some you might find compound your interest continuously, not once a month or 4 times a year or 6 times a year or even once a year, but continually, every single second. They're computing your interest. This formula is a little different. Look at the formula. Your amount A is equal to, again, the principal, what you put in, times E, and we all know that E is an irrational number approximated by 2.718. E raised to R, the interest rate, times T, the number of years that you're going to leave your money in the bank. Okay, and that's what the variables are spelled out here too for us. N is the number of compounds per year, T is the number of years. So let's look at some examples of these formulas. All right, we're going to complete the table to determine the balance A that you'll have for your $2,500 investment at a rate R for t years and compounded n times per year. All right, so let's look at the structure of this table. The top row, n, represents the number of times per year that the institution will stop and calculate your interest. So once a year, at the end of 1 year, maybe twice a year, maybe every 6 months. Quarterly, that's kind of common for banks. That'll be every 3 months they'll stop and compound or find your interest by using the compound interest formula. Maybe once a month. What about if a bank stops every single day of the year and calculates your interest? Or what if it's every single second continuously that they are calculating your interest? Okay, so this top row is n number of times per year that you will, they'll compound your interest. Okay, the bottom row is going to be the amount based on these different compoundings. All right, so you put in $2,500 into the bank. The bank's going to pay you 2%. That's pretty low, but it's pretty common. And you're going to leave your money in the account for 10 years. All right, so what we're going to do is we're going to do a recording for each of these n values. All right, so come down here and let's look at what if a bank only pays you interest at the end of each and every year. So when n is 1. Okay, according to the formula above, 2,500 is P. 1 is always part of the formula, 100% of your money plus, and we're going to build a fraction. In the numerator of the fraction, we're going to put the decimal form of the interest rate, so it's going to be 0.02. And for this particular calculation, we're going to let n be 1. That's our denominator. We're going to close our parentheses, and we're going to put an exponent on this. The exponent is n times t. Well, n is 1 and t is 10, so 1 times 10, or just simply 10. All right, the next thing we're going to do is we're going to go right straight to our calculator. You're going to enter all of this information just the way you see it, and then we'll record to the nearest penny, okay, the amount of money you will earn by the end of the year based on your $2,500 investment. So computing this value on our calculator, after 10 years, put a little dollar sign here, this is how much money you'll have in your account. $3,047 and round to the nearest penny, 49 cents. If you can stand to give up $2,500 for 10 years, you'll make a little over $500 in interest. All right, let's look at n equals 2. What happens if they stop and calculate your interest more often than, say, once a year? Is that going to have a significant impact on the amount of interest you're earning? Let's do a recording, okay, of n equals 2. So the formula starts out the same. The interest rate is still going to be 2%. We divide by the number of compoundings, in this case 2. We raise it to n times t. So n times t is 2 times 10, or 20. You might want to stop and go to your calculator and enter that. You can actually just recall your last line and make some edits. Your earnings would be $3,050.48. So almost $3 more if they stop and compounded twice a year. All right, well, what if a bank, which most do, calculate your interest quarterly, 4 times a year, every 3 months? Divide by 4. Raised to the n times t. N in this case is 4 and t is still 10, so that'd be 40. Go back and edit your last line. Pretty small difference between compounding once a year, twice a year, or even 4 times a year. This was n equals 4. Okay, well, what about once a month? At the end of every month, 12 months in a year, if the bank stopped and calculated your interest, what does that look like? N is 12, raised to the n times t. 12 times 10, your new exponent is 120. Stop, do the computations on the calculator. Let's see if that makes a significant difference. And actually, it really doesn't. Your A value amount is just going to be $3,053. So whether a bank stops once a year or 12 times a year, okay, you can see it's roughly about a $6 difference. Not enough to worry about the number of compoundings, okay, offered by a bank. All right, what about once a day? You'd think with this exponent increasing as much as it's doing, that would have a, a bigger impact on the amount of your earnings, but it in fact doesn't. The only difference is 49 cents once a day to once a month. Okay. And even though the exponent's getting larger, what happens is the value of this fraction gets smaller. So if this fraction gets smaller right here, raising it to an even larger exponent really doesn't significantly change the output. Okay, but what about continuously? Surely that's going to make a big difference, and surely those are the banks that you want to seek out, those that offer compounding continuously. Let's see. So that formula is PERT. Sometimes you'll hear it be referred to as PERT. PERT. P, your principal. ER is the interest rate. T is your number of years, so that's times 10. Enter this into your calculator, remembering that E can be found the second button above the on button. It's really kind of difficult to believe, but it's only a 2-cent increase if they compounded continuously as opposed to once a day. Banks are well aware of these formulas and compoundings and how it has really no significant impact. So it might be a selling point for them to say to you, hey, put your money in our bank because we're going to compound it continuously, making you think that maybe your $2,500 is going to go to $25,000 when in fact it's not even going to be close. Okay, you really want to seek out a bank that has a higher interest rate. That's where the most impact's going to come from on your earnings. Okay. All right, so let's look at another example. In this example, we're just going to look at compounding your interest continuously. We're going to use the PERT formula in all of these T values. All right, so the difference here is we're going to find the amount A for your $12,000 that you're investing at a rate of 3.5% for T years. So I don't need to know N, the number of compoundings, because N is not involved in your A equals PERT formula. Okay. All right, so T represents the number of years. So let's look at T equals 1 year. $12,000 E 0.035 times T, because it's R times T for this formula, in just 1 year. Go to the calculator, perform your computations. All right, so the result if you can stand to give up $12,000 for a year after 1 year compounding continuously, you will have earned a little over $400. All right, what if your number of years was 10? So if you can give up $12,000 for 10 years, let's see what your $12,000 will do in that amount of time compounding continuously. Go to your calculator, do the computations. I'd say that's pretty good. If you can stand to give up $12,000 for 10 years, you'll make $5,000. Let's see what happens to your $12,000 investment after 20 years. And this is times 20. The amount in your account will be a little more than double, $24,165.03. What about after 30 years? almost triple your $12,000. So your guys' age, at your age, if I was you, I'd try and find $12,000 and put it in the bank, and at least find a bank that compounds your money continuously, because you've almost tripled your money. After 40 years, you've quadrupled your money. And after 50 years, at about the time you're ready to retire, your $12,000 is now at $70,000. I think that's a pretty good deal. It's just the problem is, how do you come up with $12,000 right now? All right, anyway, I wanted to go through applications of exponential functions, because exponential functions play a big part in our real world. We can use exponential functions to not only calculate interest, we can use it to predict population growth, population decay, and many other things as well.